All right, welcome to the second part of the AcqVA Lab workshop on power analysis with R. So we thought that we should start off with a Q&A. And also I asked Serge, if he would like to contribute some things, because as you know, he's also very good in stats, very good in R. So I wanted him to also raise his or contribute a little bit. So he has to say something about effect sizes, because that seems to be an issue here for many people. So yeah, take it away,
we just
Serge.
talked about this a little bit in the break. So I just had the impression that I think one of the hard things to realize about this kind of power analysis, the things that Martin talked about in the beginning, is that there is no fixed algorithm or fixed procedure to determine what effect size you should include in your power analysis. It's not an exact science. It's basically an informed guess. So what kind of effect size you would expect based on all sorts of information, whatever information you have. It doesn't have to be exactly, you don't have to have access to exactly the same type of study as you're planning to do. It might be just, a range of studies in the same field, basically, which you can look at, and then you have a general impression of what kind of effect sizes you have in that field. And from that, you can perform a power analysis. So it's not, there's no fixed algorithm on how to do this. And I think that's one of the maybe things that are a bit harder to understand about this. So you just need to be able to roughly justify why you choose this kind of effect size for calculating your sample size and not a wildly different effect size. But you don't really have to justify the precise number, and you almost never can justify the precise number.
And also,
so yeah.
When I took my little walk, my stroll around the block here, under the palm trees, I also had a thought, namely, like something that is important to understand is, like, you run a model, right? And you find a significant effect, right? And then all is good, because essentially you have found an effect, right? You can be very confident, okay, there's something there, right? The problem is really what happens if something is not significant, right? That's really the problem, because the fundamental question is it not significant because there's really no effect, right? Or is it not significant because the sample size wasn't big enough, right? That's essentially the main question, because if you find an effect, okay, that shows your sample was sufficient to find that effect. But the problem is rather when you don't find something, because then you need to determine what's the cause of not, finding that effect. And now the point of setting the effect size too low, like what I did, was to basically justify, okay, that interaction returned as being not significant, right? But my data, for example, if you have enough data, my data is sufficient to find, for example, a small effect with 95% confidence. And that means I can confidently say that it was returned as insignificant because there's really no effect, right? So that's basically the way to look at it. So rather than basically thinking about it in terms of significant effects, is rather how can we, what do we do with insignificant effects, right? And that's really going right back to the question that Marit raised in the last AcqVA lunch talk, right? Because she said, well, maybe there were not enough items, right? And she was right. And now power analysis would actually, tell us something about that, right? Do you have other questions or comments? Oh, I want to say something about Judith, because you also turned on your camera. Thank you for that, by the way. That's awesome. So, okay. So with respect to effect size, right? You basically mentioned, yeah, okay, you're using odds ratios there, but what about if you use a different scale of variable, right? And so, for example, if you have a numeric predictor, because then obviously you would, probably have a different effect size measure or something like that. And then scaling always plays a role. So typically when you have numeric predictors, you should scale and center them, right? Because otherwise the predictions are kind of oftentimes meaningless, and you want to predict not for 0, but for the mean. So then basically you center and scale it. And so the predictions are for the mean of the value. And then you'd really have to basically check, with the standardized beta that you get. So you get an estimate, you convert that into standardized beta. And then you can again see, okay, what with the standardized beta, what effect size is that, right? And then you can again set it, and you can set it to, okay, the standardized beta that is equivalent to a small effect. And then you basically do the same thing that we did here with the odds ratios. Is that clearer? Did that answer your question? Or wait, did I misunderstand it in another way?
Yeah, so first of all, probably what you said was correct at this point, because I was wondering, so if I have a categorical variable, then I should take into account that it's on the logit scale, right? Well, but on the other hand, we had no dependent variable in this example. So maybe it was also a misunderstanding from my side. But typically, if you try to interpret something, you have to, well, consider what is the scale here. And so I was wondering whether this is something I should consider as well when doing this step here.
Yeah, so actually the problem with the dependent variable is actually not that big of a deal. Actually, we'll address that, like seriously, because we'll look at a G-Elmer in the next example that we're going to look at, right? Is there anything else that you'd like to talk about? Anything that you're unsure?
Yeah. Can I also make a little comment about the last part that you did with the simulations? I don't know if it's a comment or maybe a question. I don't know. So it's about the. So I was wondering if we could maybe dig a little bit deeper into the syntax of this power sim function, and specifically about the fcompare, the test parameter, right? Because I feel like maybe I missed it, but I don't think you kind of talked about this, and I think there's a little bit of confusion in the RMD file. I think there's like a typo or something.
All right.
So yeah, so as far as so if we look at your at the first time where you do this power sim, right? It's power analysis section.
Yeah.
So your test is, you're comparing, so your test is uses this function fcompare, and as far as I understand what it does is you define an alternative model to the one that you have defined previously, right?
Yeah.
So basically, in this case, you're comparing the model which includes the main effect and the interactions of group and sentence type to a model which excludes that and just has one fixed effective word type.
Yes, you're actually right.
You're not just testing the interaction, you're testing also the main effects of group and sentence type as well, right?
You're actually right. That's an error on my part. You're actually right. I basically, yeah, I can only apologize. That's true. So you essentially create a separate model and then you compare the two models. So Sergey's is correct there. I basically,
yeah, and I think it's even more kind of important in the second type. So when you do power analysis for interactions, right?
Yep.
Later on. So I think that what you're doing here is actually you're testing the main effect of word order, because your alternative model, right, includes an interaction of group and sentence type, but excludes word order, which was in your original M1 model.
Yes, you're right. I think, just give me a second.
Here you're not actually testing for the interaction, you're actually testing for the word order fixed effect.
Yes, I think you're right.
I don't know. Maybe I'm
talking about, Serge?
So I'm talking about, so if you look at the power analysis for interactions paragraph in the RMD file.
And just approximately, like what line number is that?
That's 564. So maybe I can, yeah, maybe I can share the screen.
Because it's an asterisk rather than a colon, Serge.
Sorry?
Because it's an asterisk rather than a colon. So you're
No, no.
looking at.
No, he's making a different point. So he's
So
making.
now I'm so it's line 564, right?
Shall I share, or would you like to share? I completely
Yeah,
get what you're
maybe you
saying,
can
and I think you're right. Okay. Let me share this here. All right. So previously I had a different command here. I just corrected that, right? So Sarah's point was that we created a model here, right? And the model looks like this. So the model is that we have that we predict y based on a random random intercepts for sentence, then group, right, as a main effect, and an interaction between group and sentence type as a main effect, and word order. So that's the model that we have, right? And Serge is right. It's actually my mistake here, because what we do is here we compare the model that we have, this model, to this model, right? That's what you mean, right? So you compare this M1 model to this model. That's what you mean, right?
Yep.
I think you're
so
correct, yeah.
So what you're testing the power to detect the main effects and the interaction of group and sentence type in this case.
Yes.
And then in the second one, which you have now modified.
Yes.
Yeah.
So this would be the one what you mean. If you wanted to test the interaction, then we need to use this.
Yeah.
Yes, I think you're right. That was my mistake.
Yes. So in the AcqVA thing, you don't put the things that you want to test for.
Yeah.
Right. You put everything else to the exclusion of the thing that you want to test for.
Yes, I think you're right. I can tell you why, because I had a different test here before. I had the z-test, right? And the z-test tests for a specific predictor. And so I just copied and pasted. That was my mistake. But I think you're completely right. So do you understand Sergei's point?
So it's kind of like when we do like the drop, like drop
Yes.
one kind of thing, right? Yeah. Okay.
Yeah.
Exactly. It's model comparison.
Yes.
That's why it's called AcqVA. It's the same thing. It's model comparison.
Right.
Yeah.
Mm-hmm.
Yeah, Sergei's right there. So apologies for that. Have a look at what I do in the updated one. So this would basically be the correction where we check for the interaction. The point remains though, right? So the point remaining that the model has not enough power to check the interaction. But yeah, that was actually a brilliant point. So thanks for that. That was actually very, very helpful, right? Okay, so you need to specify basically everything else and then basically leave out the effect that you're interested in, right? And so you compare the model with and without. So it's like, yeah, comparing the models, and then that gives you the power to find that effect.
And then may I ask just why we don't specify the intercept here again?
Because here in with this specific function, this tells you that you only need the fixed effects part of the model. Like the random effect part will just basically copied from the other model. So you don't need to specify it. All right, cool. Just to recap before we continue, and Serge and everybody else, if you find me making mistakes, please tell me. It's not because I'm mean or I want to make mistakes. Sometimes I just like to copy and paste, and sometimes I just don't know any better. So I really don't take it as an affront or anything like that. I'm actually very happy when you point something like that out. All right, so what have we done before? All right, so first we started off with basically checking how different concepts relate to each other, namely effect size, significance level, variability, and sample size, right? And we found out that basically you can use these parameters to calculate the power when you have a very simple model, right? Then basically we talked about, okay, that is not really possible when you run more complex models, because then the only thing you can really do is basically work with simulations. And that's where we are, right? So now we've created a mixed effects model, right? A linear mixed effects model, where we just use the predictors, and then basically we set the parameters and basically created a model based on the predictors and the parameters to come up with basically a model that we used to then determine the power that it has to find certain effects, right? And here for the final model, right, compared to this model, so to find all the other effects except for word order, that should be right now, right? That would be very high, right? To find the difference in those models would be very, very high, because the other model just explains a lot more variability. And so that's easy to detect, so to say, right? And then I explained why I set the effect sizes to 0.52, because the effects that we have here, the estimates can be converted into odds ratios. And for odds ratios, we know the translation into D values. And so we basically know what is a small odds ratio, what's a medium-sized effect size for odds ratios, and what's a large effect for odds ratios, right? And here I chose to include small effects, right? Okay, so you have that here as well, just as a recap. And now this was the point where Serge basically said, okay, there's actually a problem with fcompare, where I basically copied from the z-test, and he's right. So here we compare the model that we have, which has an interaction between group and sentence type, to the model without it, and the power for that is not high enough. So if you look here, we find that the interaction between group and sentence type is not significant. But given the low power, we don't know whether that's because we don't have enough subjects or items, or whether it's because there's really no effect. So what can we do? The next step is we extend the data, right? That means we have the data set that consisted of 20 subjects, right? And those 24 sentences. And now we want to increase that. We want to increase the 24 sentences to 50 sentences, and then see if that's sufficient to basically find the interaction. And so I need to correct this too. And now we can check. And actually, I should really make this a little bit higher. I know it takes a little longer, but I want to have estimates that are not completely off. And as I said, you should actually use 1,000 at least when you do this, because the estimates here are still not very accurate. But it would take ages if you used 1,000. Okay, so with 50 sentences, right, and our 20 subjects, we have a substantively higher power, but it's still not powerful enough, right? So what you could do is you could now check, okay, let's take 100 sentences, right? And then check, okay, do we have enough power now? Dum, 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 dum. And while we're at it, I should say something about this. So I mentioned it before when we talked about the when we were in the data visualization workshop, right? So what I do here is I suppress warning and messages, and I did this basically to make the rendered document nicer. But actually, when you run simulations, you should actually have the warnings and messages in here, because what happens is that oftentimes you get error messages for models. And when you turn off the messages and the warnings, you basically don't see that, for example, your models did not converge. And so you get basically an estimate that's completely wrong, right? And you maybe don't know why. And that could be because you suppress the warnings and error messages. And so you don't know what went wrong, right? And so it's actually recommendable that you get rid of the messages false, warning false here when you run simulations. So now we're actually pretty close, right? So we're at 77%. So now we know that with 100 sentences, right, we would be almost there, right? So if we had only 20 subjects, so for example, you can only get your hands on 20 subjects because there's only 20 bilingual Russian Chinese children who acquire English or Norwegian as a third language in Tromsø, right? So your pool of participants is limited, right? Then you can use this to basically check, okay, how many sentences would I have to include in my study to have sufficient power given the number of participants is what it is, right? Because I can't do much there. So that would be one way to do that, right? And if we now increase that even to 1 in 20, we can extend the data set. We run the simulation, and then we'll hopefully find that then we'd breach the 80%. Again, 80% is kind of arbitrary. If I were you, I'd actually try to achieve a higher power, right? But in the papers that I wrote, where people asked for power analysis, or where people basically doubted that the data was big enough, I used 80% as the cutoff. I referenced the papers that I also mentioned at the bottom of the document, and that basically satisfied the reviewers, which was fine for me. All right, and now we see with 1 in 20 sentences, we have enough power, and the confidence intervals are above 80. They actually include 95%. So in this case, that would be what you could do. Here we have a question: how would you estimate power for 100 sentence distributed across 4 subjects in 4 lists? That depends. So what I would suggest that you do is really to come up with the data, like really properly the data that you would expect. You can do that in Excel, you can generate that in R, and then really just test it. You really just simulate it. So I can't answer the question. I'd really just set up an example data set that would be very much to what I would expect, right? And then I'd run the simulation, and that would give me more information. Okay, now there's something that's very handy. Namely, you can also create a power curve. And the advantage of a power curve is that you don't need to do this basically iteratively, right? You can also say, okay, I want sentences to, or show me the power with the confidence interval for 10 to 50 sentences, right? And because we've more, let's say 120 from 20 to 120 with 20. So this means create a vector from 20 to 120 with intervals of 20. So we'll have 20, 40, 60, 80, 100, 120. So that's what this command means. In this case, I use only 20 simulations, which is, again, not much, but I don't want this to run forever. And then what we get is the power curve. And now you see that for each interval, so for 20, 40, 60, 80, 100, 120, it basically simulates what we've done before, and then it plots it, right? And so here it actually tells us, okay, the 80% breach is already crossed with 80 sentences, right? Although we can't be entirely sure. We have another question, Janina. Thank you for this question. Or with this approach, do we assume 100 per conditions? Yes, power also has its confidence interval. It's like a confidence interval, if you like, right? And because it's really, it's simulated, right? So it basically takes data and samples that. With Janina, I'm not entirely sure what you mean here.
Yeah, and like, you know, because we always work with lists.
Yeah. So, but what do you mean by list? So you mean that every subject only sees part of the sentences?
Yeah, like, you know, if we have 4 conditions, and if in our design, we had 100 sentences per condition, we then counterbalance everything so that each person sees 1 item in only one of the conditions. So I guess with this model, if we specify number of sentences 100, we mean it's like per list. Like we don't really take lists.
Ah, right. Actually, I wouldn't know that. I couldn't answer that right now. I'm very sorry because I basically don't work with that. I can't answer that on the spot. My suggestion is always to basically come up with a data set and then try it out. But I see a problem because not every subject is actually, yes, so you'd okay, I'll answer that question in a second, right? My answer would be to really try to maybe then come up with a data set that is very similar, where not all sentences are shown to all individuals in the fake data set that you create, so to say. Because you have this kind of matrix like this in Excel, right? Where you have all the conditions and how they are crossed with each other, right? And I think you could in principle still use that for power analysis. But in terms of how to implement that, like the code that you need would have to be extremely similar to this, but I'd have to look at it. I can't tell you out of the top of my head. And yes, so the question about subjects nested within groups of items sounds great. And it's probably the right random effect structure. I'm pretty sure it is. Just in this case, with the data here, any other more complex random effect structure didn't work. Because then you get too many warnings, and then basically you find that the power is 0 because all models fail to converge, and then I couldn't show you anything. So I wanted to show you a simple data set and then show you the procedures so you have an idea what's going on. But you'd have to fiddle a little bit and dabble with the code to make it work for your analysis. I can only show you how it works and the different steps and the functions that you can use. But it will be a little bit different for your own experiments. All right, so here we see the power curve that I just showed, right? And
Can I
now,
ask something?
yeah,
Is it,
sure.
Usually the case that you get like this big jump between, well, in this case, 60 and 80. Can you show the graph again?
Yes.
No, below.
This one.
Yeah, so it's like from 20 to 40 to 60, there's almost no change, and then suddenly.
Yeah, actually, I think that's because we have only 20 simulations here. If I do this, actually, I think it will be smoother. But let's find out, right? So let's check. It'll take a little while now, but I think this is that's probably an artifact, I would guess.
Okay.
And if it's not, then that'd be interesting. An intriguing result. Right. So let's
I can imagine that if once you like reach some sort of threshold, it doesn't improve as much anymore if you keep adding sentences. But
yes, but that didn't explain that kind of increase, right? Because you would actually expect something like this, and that's what you also see when you run thousands of simulations, right? So that's why I think this is basically a result of running too few simulations here.
Okay.
And again, 100 is not enough. But I mean, if we did 1,000, we'd be stuck here for 15 minutes at least.
Okay.
Right. Maybe not 15 minutes, maybe 10, but it would be pretty boring. Right, see? And now the jump is gone.
That makes much more sense.
Yeah. So you have to excuse that, but I just want to avoid, waiting too long for the simulations to run through. So the results have to be taken with a pinch of salt, right? Okay. So here, basically, I wanted to check, okay, what do we do if we don't want to increase the number of sentences, but we want to increase the number of participants, right? And here, basically, we do exactly what we did before. We generate another model, same as before. And now here, we can actually do the proper one that we also used above. Let's just copy this. And yeah, that was just a stupid error of mine. And here we see, okay, given what we have, we 40% power, not enough. What did I do here? Oh, I just showed another way to do to test the effect of word order v3 here, and that would be 80%. So here, if I understand it correctly, the paper that introduced the simr, actually this would really be this effect. But Sergey, would be great if you could actually check that. But I think here you really want to test the power for this effect, because you have to specify the level as well, right? And in this case, with 10 simulations, you get here, right? Again, we can run a power analysis. So here, the thing is, we still don't have enough power. Here, for this one factor, if we want to test the power there, it's sufficient. So here, no, here you the fcompare again. So here's the other way around. You need to copy this. Sorry. I know there's
Martin,
some.
Can I ask a question? What's the difference between doing that type of model comparison type of approach versus this approach where you put in the effect that you want to see?
The difference essentially is that here you test just one factor. At least that's my understanding.
But you can't test one, like, not like a level, but like a condition, like group or sentence type?
Yeah, here it is. So here it's basically what's the likelihood of basically finding an effect for switching from V2 to V3. That's the idea that I have here. So it compares within word order.
Okay, so basically, if there's two levels, then it's basically like looking at word order.
Yeah, that's my understanding.
But what if there's like 3 levels, for example?
Then I basically check, let's say, I know it's not possible, but let's say this, right? And then it would tell you what's the likelihood of finding switching from 2 to 4.
Okay, so it's always like the reference versus the whatever you're looking at here.
That's my understanding. Yeah, could be wrong, but that's basically as far as I can see, and as far if I understood the paper correctly, which I think makes sense.
So is the power sim in the above one more like looking at the main effect, whereas like the one here is looking at like level differences, or because I'm kind of a bit confused.
Yeah, so here you also test effects, right? So you also test basically what's the difference between the model with the interaction to without the interaction. And you could do the same thing with one individual predictor, right? The only issue is that up here we defined the model not as the null model. Oh, sorry, where would we define it? Define it here. So we defined our M1 model to have this call, right? The structure. But you could also use a different structure here, right? Only we started out with this kind of model specification with a complex model, right? But you could also, for example, say, okay, this model only includes group, right? And then, for example, here you want to have group plus word order. And that would then tell you, okay, what's the difference between a model with group to a model with group and word order?
Right. Like, so you can do the subtraction method or the addition method. It doesn't really matter, right? But yeah, but my question was more like for this one here with the level comparison.
Yeah.
Yeah, I don't understand. Well, my understanding is that like the first one, you really want to check the if you have, for example, more than 3 levels and you want to see like the effect of that one factor, then you can do that one. But if you want to see for example, whether, yeah, as you said, the power of the difference between the levels itself within a factor, then you use this, or
no, this stands for this. So this is really one predictor in the model, right?
Yeah, but that's because it's 2 levels, right?
Yes, but in the other level is essentially in the model because it's included in the intercept, right?
Right.
So the intercept basically includes all the baseline stuff, right?
Yeah.
And then we check, okay, if we include this, right? This predictor with this strength, what's the power of finding this effect, right? And that's a certain amount of power. Now, if we had more predictors, right? Or more levels, what would happen is that we'd not only have word order V3, we'd also have word order V4, right? And so you can then check, okay, do we have enough power to find basically a difference between what is in the model and this predictor included? At least that's my understanding.
Right, but then the interpretation becomes different from the first one where you just include word order plus word order and group, because then that assumes that if there's like 4 levels in word order, whatever it is different from word order and group, right? Whereas here, like right now, it's kind of the same interpretation because you have 2 levels for word order.
Yes.
Is what I'm saying.
Yes.
But if there's more levels, then it becomes a different interpretation, because the first one you just do like group plus word order versus just word order, and you look at or group plus word order plus versus group, and you see the effect of word order. But this one, if there's 4 levels and you want to compare, like if there's V1, V2, V3, V4, and you want to, V1 is the intercept, you want to compare V1 to V4, then you would do this type of thing. This would be more appropriate.
I think so. I have to say I have problems understanding. Sergey, do you know?
Yeah, I think Maki is basically correct. I mean, it's the same as when you simply use mixed effects models or just linear models, right?
Yeah.
You can look at the model output. And
exactly.
You can see the p-values in the model output, right? For each fixed effect. And if you have a categorical variable, for instance, which has 3 levels, then you'll see the p-values for the difference, and your variable is dummy coded, because it also depends on what your coding is, right? So if it's dummy coded, then for each level, you're going to see the significance of the difference of all the other levels compared to your base level, to your control level, right? That's going to be your model output. And that's what you do with the second method, right? You test, like you said, basically, right? You test the power to detect a significant difference between a particular level and the baseline level, if the variable is dummy coded. But if you just want to test for the overall effect of a particular predictor, then you do model comparison. But again, like you said, when a categorical variable just has 2 levels,
it's the same.
It's more or less the same thing, right?
Am I
but if
missing
you
something
have 3
here?
levels, there is an important difference.
Yeah.
So basically, the fcompare would basically be like the ANOVA call that compares the factor as a whole. And this would be basically the different levels. Yeah, makes sense. Yeah.
Okay.
Is that what you mean, or?
Yeah, that's exactly what I meant. Yeah.
Okay. Right.
But how do you like then? Right. Okay. Yeah. Okay. So the coding procedure would be the same as how you would do it in a normal model, right? Like if you wanted to sum code it, then, or like whatever coding system you use, it's, even if it's a dummy, it doesn't matter because the independent variables the same as in.
But I mean, it doesn't really matter what type of coding you use in that case, because if you have here basically if the intercept is 2 versus 3, right? And then you have
Yeah.
another coding which has essentially two, like let's say word order v3, word order v2, right, as predictors. Then you would basically compare v2 to basically what's in the baseline, and you could then compare v3 versus the baseline. I still have problems understanding that in a way.
But if it's some coding, for example, then the intercept set to the grand mean, right?
Yes.
Then it's more like a main effect like interpretation, right, Serge? So, or
yeah, I think you're right.
Yeah.
Yes. So then if you use this method, you're going to be testing the difference for this particular level compared to the grand mean. If you have a different type of coding.
So, but the coding system, works the same as like it's okay. Yeah.
But since you have your data set, or maybe your model data set, or the data set, or the structure of the data set, right? You have determined that at the beginning.
Yeah.
Right.
And you can determine the coding of the variables of the data set.
Right. So before you run the model, the first model that you showed us, Martin, then before that you can set the whatever like contrast that you want to set, and then okay.
Right, it's like basically an ordinary model where you set parameters and options first, and then you determine that. So there's a difference in the output, right? But like what I do still have a problem with is, right, here basically for me it's clear that I compare v3, right, versus basically v2, right?
Yeah.
But if you have some coding, you'd essentially have word order v2 and word order v3 here as different predictors, right? You'd have two predictors here instead of the one in the summary table.
Yeah. And
right?
It wouldn't even say v3, like it usually says like factor 1 or something like that. Yeah.
Yes.
So you like always have to check the levels, and it's annoying.
Yes, but then actually, I'm not sure if you would basically use the fixed stuff and z-test there. I really wouldn't use it then in that case, probably.
I don't know.
I would, because then I would really compare the model with and without the predictor.
I always go for that option because this reference thing like always annoys me, because I usually have more than 2 levels or like within a factor. So for me, like the ANOVA type of interpretation is, and then just run a stock test is like my type of way of doing it all the time. But it does get confusing. But I think I guess like it really depends on your research question, because sometimes, like, for example, like sometimes I do want to see specifically the difference between, like, for example, if I'm doing switch costs and mixing costs, for example, and there's 3 levels, and I always want to check, one level against the other and the third level against the first one, then maybe like this might work better because of the research questions that you're asking.
Okay.
But
I get your point.
For example, and just looking at,
okay, that makes sense. Yeah,
the difference overall in the levels, then I guess you can use the first method, and that will satisfy your questions. But
so that makes perfect sense. My question, the question I had was essentially how does that translate then into the number of estimates and what they stand for, and what's included in the intercept? But it makes perfect sense. If it's the grand mean and then you have the different levels coming up, right, then it would actually make perfect sense. So sorry, I get it now. Took me a while. All right, so but let's basically check what happens here. Now we have a problem, because now you can actually see what happens when we have a too complex model. And in this case, basically, yeah, the number of subjects, of course, here is way too low, right? And here it basically begins to rise. So we need to increase the number of participants, right? Which is what we want to do, right? Okay. Now, what we could do is we could create another, where is that? Here. We could now include a little something here where we increase a long ID, and we say we don't want to only have 20, let's say 40, all right? And I hope this works now. All right, cool. And let's copy this. Now I need to adapt this. Just give me a second. And I hope that this should basically give us a better power for subjects. So it's better than before, still not high enough. So that would basically tell us we need to still increase the number of participants here, right? So 40 is not enough in our scenario. So we still don't breach the 80%, right? And so we could basically go about increasing that further and then basically checking with the power curve, doing the same thing that we did with sentences, and check where does it breach the 80%, or optimally, where do we get values that are above 90% or something like that, right? So that we can be really certain that if we don't find something, it's because there's no effect, right? So essentially can do exactly what we did before, only with the number of sentences that we increased, using the extent here, only replace sentences with ID, and then basically can increase the number of subjects in your data and see how that works. And then basically check the power for the different number of participants. All right.
Martin, can you do the with and without model comparison type of thing with like the with and without the random effects?
I'm not sure. So you want to basically check, does it make sense to?
Yeah, like does it increase power if you include a random effect? What does that even make sense? I mean,
no. I think like in that sense, it really doesn't make sense. I think you wouldn't increase power if you included a random effect.
why would that be? I'm struggling to understand.
Because I really don't see how that would relate to any of the parameters that we talked about. Like, I don't know why including a random effect in a model would increase power.
Yeah.
You could have a better fit, right? Like the model could be better. That's perfectly fine, right? You could have a better model, and you could compare a model with like one random effect structure to another random effect structure, and you can compare the models and see which model is better. That's granted, right? Like, and you can compare, you can compare it in different ways, but I don't think how that would affect the power.
Because if I recall correctly, not using simr, but like another, like they made a website, like what was it called, Power or something, with linear mixed effects model. And I remember entering something about random effects when I was using, it's like, it wasn't like this type of thing where you have to do it in R. It was like a website. Does anybody know? Like it was, I can't remember. It's like another website of calculating
Judith
when
just
you're-
wrote G-Power. That's actually a very popular site for calculating power.
Yeah, maybe, maybe it was G-Power, yeah.
Okay, I can tell you.
But I
Yeah,
don't think power has linear mixed effects. It has like simple stuff like ANOVAs.
Yeah.
there was a website, I forgot, maybe I'm just imagining it, I don't know.
I can tell you where I see a potential problem, and I could have shown you here if I commented, if I basically used the model with the more complex random effect structure. Let me do that for a second and just show you what happens, because
Okay.
maybe that helps. So here you see I commented out a model. You see that?
Mhm. Yeah.
And let's comment this out. Let me get rid of this. Actually, I won't comment it out. I'll just run this model. Oh, yeah, sorry. And here, this is called word order now. Yes, and then I need to, sorry, this is the live coding shit I was talking about. And then I go here, I run this, and now we have a model, right? We can have a look at the model. And now we have two random effects, right? One for sentence, one for ID. It's still not optimal because it's not nested sentences within ID or something like that, right? But the important thing is that if we now run this power simulation on model, and let's say 20, just for the fun of it, you'll see something weird happening. No, that's actually the same as before. I want to show you something where it broke down, and I know it broke down because I tried it out with some stuff. So you get really weird power curves when you do that, because when you have then models that have singularity, they basically feed into the calculation as 0. And that happened when I used the more complex random effect structure. Again, no errors, no warnings here. But I tried it out. At some point, it really didn't make sense to include it, to include a more random, more complex structure. I don't know where. I tried it out, and the thing is, then you get like these really weird graphs where it sometimes converges and sometimes not, and then it really jumps. So what I could imagine is that when you change the random effect structure, that led to more models basically not converging or converging, and depending on whether they go into the calculation or not, right? That would really affect the outcome, right? So there you really see a difference in power, but that's not because of the power. It's basically just because your models fail to converge. And then you can include them as zeros or as NAs. And if it's 0, right, you'll have a very strong effect because it's really counted. When it goes into as NA, you might have only 2 models. And then basically your entire estimate is based on those 2 models. So that's a way how you can think of a way in which changing the random effect structure could affect the power.
And I should also mention one more thing. There was a paper, I think in 2017, about, so you probably know about this recommendation to keep things maximal.
Yeah.
Right,
Yes.
maximal random effect structure. So it actually turns out that has costs for power. So the more complex, if you include a really complex random effect structure, that means that the power actually goes down. It doesn't go up.
How? Why?
Well, I can't really go into details, but there is a paper specifically about this, and about, so when you include the random effect structure is actually there to battle type 1 errors. So what you called alpha errors, false positives.
Yes. Cecile
So that's
also
why you
writes,
include the random effect structure, because you want to include,
yes,
you want the model to understand the real structure of your data and all the nested relationships.
right.
But if you include everything, so it's like you can never get the perfect, you can never be in the perfect world. So if you include all the random effect structure, you're really good at avoiding type 1 errors. But then you include the probability of type 2 errors. So, and that means that the power actually goes down. So you have to look for a balance between.
I found the website, actually, it's this one. I don't know if anybody has used it, but it's like by Westfall 2014. And it's like a website, more like a plugin system, like with like the ANOVA stuff that you showed us, Martin.
Let me stop this for a second. Cecile also wrote that basically, okay, that makes sense, that in the sense that, okay, random effects basically eat up variability, right? So I get that. That's perfectly fine, right? And that's why the p-values basically become more conservative, right? If you include random effect structure. Fine. Still, I'm not entirely sure, like when I think about how to calculate power, how that would fit into that. I understand
the paper that I mentioned, and it has a discussion of this specific issue of how the complexity of random effects
I'd have to look at that.
Impacts power.
Because at least for the website that I showed you, I sent you, it seems like there is a section, if you look at the left-hand side and you have the effect size and whatever you want to solve X for, like how you did it in the ANOVA type of thing. And you have like the participant intercept. I mean, that's like a random effect, like random intercept, right? So that's why I was confused by that, because I remember doing, like, trying to work this website out and I didn't know how it, like what numbers I should plug in, at least for this. So, I mean, this is like a side note thing that obviously we don't have to look at this website, but that's why I thought their random effects could relate to power.
Maybe you're right. I just really need to look into that. Like right now, I'm still not sure. Like I acknowledge that people say it, but I'm this kind of weird person. I need to really understand it. Like right now, from my understanding of what's underlying it, I really have to look into it. You're right. I'm happy to acknowledge you're probably right, but I have to understand it. I don't really completely understand it yet. I really have to check it out. Right.
Okay, I don't understand. It's really complex, but at least from this website looks like you can, and you know, it's more, I think, straightforward with this website. If it's correct, you know, you just check whether or what type of like design it is, like, so it, you know, you have like cross counterbalance stimuli, like lists and stuff like that, and then whatever setting you want to do with effect size, stimulus intercept, participant intercept. So that has to be random effects, right? And then slope, stimulus slope. But I don't know, because not every, I don't know what this really does per se, because, you know, this is the only, it's not just participant and stimulus random effect that you can include in a model. So yeah, this website was like kind of what for me. And then it came to your thing with the model comparison, and obviously you can do model comparisons for fit in with and without random effects. So yeah, I don't understand how it wouldn't affect power, but yeah, I still don't really get it either.
Serge, I'm not sure that the paper that you linked to shows what you think it does.
Well, it shows that if you include a really big, well, at least I don't think it's that much of a theoretical paper. It's also a simulation paper.
Yes.
And they show in a number of simulations that if you include the maximal random effect structure, the power goes down often in many cases.
Yes.
Maybe not necessarily, but in many cases it does. So there is a price to having a maximal random effect structure. And they propose, I think, I read it some time ago, so I don't really remember the details, but I think they propose some kind of algorithm for finding a compromise to deciding, for instance, which random effect include, which not.
So you're saying that random effects should affect power, and so we should be able to simulate this as well, right, Serge?
I guess so. Well, I think the paper shows that it does affect power, but in the kind of in the opposite direction that you mentioned, because you asked whether if you include random effects, the power will go up. But in fact, what happens, at least if you include a lot of random effects and really complex random effect structures, the power may go down.
Mm-hmm.
Okay. The problem that I see that they argue for, and they use the random effect structure to argue against basically keeping it maximal because that has problems. But I think the point that they're making is that the problem lies in the complexity of the model. So they essentially argue that if the model is more complex, you lose power, right? And how they achieve complexity is by basically having a very complex random effect structure.
Mm-hmm.
Now, the point is not necessarily the random effect structure. The point is the complexity. That's my point.
Maybe, but still, it's a way that random effects structure or the type of random effect structure you include affects power, right?
Right. So yes, if you make your model more complex, it has less power. All right. And if the complexity comes from the random effect structure, yes, okay, fine. I buy that. That's good. That's an argument. All right. Cool. Shall we go back to the workshop?
Sorry.
No, I think it really makes sense, right?
But then how would we test it is the question, right? How would we test through this? Can you do it through this power sim thing, or?
I'm pretty sure we can. Only I haven't tested it that because I didn't consider whether I should check the whether I should check that. I
mean, it doesn't have to be now, Martin. Sorry.
No, it doesn't make sense to do it now. But the problem here is that we'd have to look at the test argument of that function. And right now, the default is that it only looks at fixed effects. So at the top of my head, I can't tell you. We'd really have to look closer into that. And I think it doesn't make sense to do that at the moment. Let's just continue, see where we get. But still, I think it's important to talk about things, right? Also to make things clearer for everybody. It makes sense to discuss stuff, right? And that also helps to understand complex things. All right, cool. So where are we at? Basically, where we're at is that we looked at how to increase, or what happens if we increase sentences, and how to basically check what happens if we increase the number of participants, right? Now, the point is that the model that we created, the first model that I created, only contained sentences as a random effect structure. And then what you need to do is to increase the number of subjects in a model. No, you have a model only sentences, random effect structure, then you increase the number of sentences, see what happens. Same thing for subjects, right? You create a model with subjects and random effect structure, you increase that. Optimally, your random effect structure should, of course, reflect the data, right? Only that I got too many errors here, that it really didn't make sense to basically have a nested random effect structure where we have sentences within participants, right? If that were the case, then you would only need one model, but it didn't converge in my case here. All right, so here I showed you how to do that, and I need to share again to show you where I'm at. Right, so here we had the thing where basically we see, okay, we actually need more subjects. Even 40 is not enough. Let's continue with binomial mixed effects models real quick, right? So what I did here is I just basically simulated the data set. I call it simdat. And what I did here, I created 200 data points, right? 2 conditions, very simple again, because I wanted to keep it simple. Test and control, 10 subjects and 10 items, right? And so I want to have a data frame. Subjects, I want to paste subject 1 to 10, and I want to repeat each 20 times. So you'll see subject 1 for 20 times, and then you'll see subject 2 20 times, and so on, right? And then I want to basically have control 10 times, and I want to have test 10 times, and repeat that 20 times, right? So control 10 times, test 10 times, and repeat that 10 times. And then that's also how you get to basically the 200 data points. And so each subject, because each subject is repeated 20 times, it has 10 controls and 10 tests, right? And then basically I had items where it just said repeat 1 to 10, 20 times. And if you do that, you basically have a data set like this, where you have subject 1, control, item 1 to 10. And then here you have subject 1, test, and then you'd have the items 1 to 10. Only 15 things here. If I run that, you'll see that now basically you have items 1 to 10 in the test condition, right? Okay. Now, to keep you occupied, I'd like you to create a data set, right? Only that I want you to have not 10, but 5 subjects. And I want to have 5 items for 4 conditions, right? And you can look below, please don't, right? But probably if you're working in here, you'll see it anyway. That was suboptimal, because probably if you look at this, you'd see the exercise and not see the solution. Yeah, so it should look like this, but yeah. The reason why I wanted you to try this out is just to basically see if you can come up, or if you can generate data sets, right? Because it's actually very useful if you're able to come up with fake data sets. You can do this in Excel, of course, as well, right? What most of you probably do, right? You sit there and basically come up with a matrix for the experiment like that. You can also do that here, right? And this would be a way that you could do that. Maybe I should go through the solution, right? So I basically create a vector where I paste together item and then 1 to 5, right? And I want to repeat that 4 times. So 4 times item 1 to 5, and then I repeat that 5 times, right? So the rep always means repeat something, and then the second part of the argument is always the number, right? Condition, I wanted to first repeat condition 1 to 4 is pasted together, and each 5 times. So you have condition 1, condition 1, condition 1, condition 1, condition 2, condition 2, condition 2, condition 2, and so on. And then repeat that 5 times. And that's also how you get to the to the length of the data set, right? And here, same thing, I wanted subject 1 to 5, and I wanted to be each repeated 20 times, right? And then you basically bind these 3 vectors together into a data frame. And then if you look at the data frame, basically you see that now you have subject 1, item 1 in condition 1, subject 1, item 2 in condition 1, subject 1, item 3, condition 1, and so on, right? And because we've only 5 items, right, this would be in condition 1, and the 5 sentences in condition 1, here of condition 2, and the items in condition 2, right? So when you want to basically generate data sets like that, it's basically just making sense of rep and how to paste stuff together, right? I think that is quite useful to basically play around with that. But if you're more confident or comfortable doing that in Excel, that's also perfectly fine, right? It's just that I try to work within R as much as possible. All right. In this case, we can do the same thing, but now we generate a different type of model, right? So here we only need to have the random effect structure and the fixed effects. We don't need the residual deviance, right? And now instead of using Elmer, we're using make G-Elmer, right? And here we do the same thing. Only here I actually included subject and item as random effects and condition as my fixed effect, right? So that explains why I only have 2 fixed here, because one is the intercept and one is the condition, right? Condition level that we test again. So this comes here. Then now the random effects, they have 2 parameters here. This would be if you only had 1, right? So here you have to basically put in the amount of variability for the 2 random effects. So for subject and item, right? And if we do that, we have, what problem do we have here? Oh, okay. I hadn't executed the code. And now we have exactly that. Again, we have the odds ratios, right? That we set here to have small effect size. We have 2 random effects. We have very low explanatory power of the fixed effect. And we see that it's not significant, right? And now the question is again, okay, is it because of because condition doesn't really have an effect, or is it because we don't have enough power, right? So this is the same thing as before, only now we're using a binomial mixed effects model, right? And here we see, okay, our power is actually way too low, right? So we can only find an effect of condition test with a probability of 35%, right? So the fact that here we have an insignificant p-value for condition is actually not saying much, right? One thing I should add here, here in the make G-Elmer, is that here we specified family binomial. You can also use family Poisson, pseudo Poisson, and all the different versions of generalized linear mixed effects models. All right, now here we can extend the data, right? So here we want to extend along item. So now we're not using only the 20 items, right? What was it? Here. No, not the 10 items, but now we want to use 40 items, right? So let's check that. Hasn't done anything really, right? Let's see what happens if we plot the power curve. That doesn't look good. Oh no, it's actually nice. All right. So here we can see that if we keep the subjects constant, right? So if we have the 10 subjects, right, then we need at least 35 items, right, to breach the 80% power threshold, right? And again, 20 simulations aren't enough. I just don't want to increase the number because it would take too long, right? So what you do here is basically you really increase the number, right, of the things that you'd like to extend on, right? Can be participants or subjects, can be items. You basically set a number, and then using power curve, you can basically check, you know, where does it cross the line? And then you can basically check in more detail and increase the number of simulations, right? Okay, now we do the same thing, but we're not increasing items. Now we're increasing subjects, right? Same thing, we increase subjects to 40. All done, doesn't change anything there. Let's check this. Same thing as before. And now basically we get the answer to, okay, what do we do? What happens when we increase the subjects to 40, not the items? Right. So here actually, if we have 25 instead of our 10 subjects, that would even be enough, right? To check if condition is significant or not, right? Okay, so that's basically how you could check either of the two. Now here comes something that's important to remember. When we extend along subjects, right? When we look at the data that we generated in the first place, here, you basically see that each combination occurs only once. We only have subject one, test one, item one once, right? Here, this combination or this configuration only occurs once. So everything here in this data set occurs only once. And when we say extend along, it will basically add at the end, right? It will add more subjects, right? And just extend the data set in that way. But each combination or each configuration still only occurs once, right? Okay, I thought that yeah, we have this here, right? Now there's another way to do that, because you could also show the same sentence to a subject more than once, right? So that not every configuration occurs once. So here, basically the way to basically add how many sentences are shown to each subject. So how often does the configuration occur? We can also increase that, but then we don't use along, we use within, right? And then we set the number of how many times, right? And now if we do this, that's of course very different. And remember, each configuration now occurs 10 times, right? So we have the same number of subjects, we have the same number of items, but now the configurations, like the combinations are basically repeated, right? And then you see that basically we have the same number of subjects and items, but if we show each item to each subject 8 times, then we also have an increase in power, obviously, right? So that I thought would be relevant to you to know as well, all right? Okay, now here's something that I think is very relevant to you, because now we come to the question, okay, I showed you how you can increase the number of participants, and I showed you how you can increase the number of items, right? But I didn't combine the two, right? And here, one way to do that would be to basically, in a first step, extend the data set along subject, and then basically use the result and extend along item, right? And now, when you plot the power curve now, what you see would be how many subjects do you need if we have 30 items, right? So if we increase the items to a certain number, how many subjects would we need then, right? So this is essentially, giving us an estimate for if we increase something, how many subjects would we need. I think that's quite relevant if we pilot on a smaller data set, right? And then here basically you have the number of subjects with crossing the line with a number of simulations here with 10. So given that we've 30 subjects, we actually only need 10 items, right? That would be a way that we could test that. Right.
Martin, can I ask a question?
Yeah, sure.
If so you've only looked at like independent categorical factors like condition and things like that.
Yeah.
But if you want to see, for example, whether, I don't know, age affects how you react to different condition levels, then you would just generate a random set of age variable and then interact that and then do the same model comparison, or run the same thing, or?
I think you'd run the same thing, but I'd have to test it first. I just haven't included here, not because of, I just didn't do it.
Okay, but even if it's not an interaction, it's just if you're looking at effect of
numeric factor, yeah,
numeric factor, you would just generate like random numbers and then plug that in the same way as these like where you have condition.
I'd have to think about it. I think I would.
Okay.
I'd probably.
And does the Z?
But I wouldn't use random numbers. So I would probably really try to basically have a look at what sample I would expect, and then basically try to have the age stratification as close to the sample that I would expect as possible.
Right.
So I wouldn't just use random numbers. I'd really try to model it as closely as possible.
And what does Z stand for? I forgot to ask you.
So Z is basically when you have the normal distribution, right? Mm-hmm. You have basically the Z scores at the bottom. So Z of 0 would be exactly the mean. Then +1 would be one standard deviation from the mean. -1 would be -1 standard deviation. And you can basically, if you have the mean and the standard deviation of any distribution, you can convert that into a Z value, right? And then you can basically check for a Z value, what's the probability associated with a certain Z value. And so you can basically say, if you have a Z value of, let's say, 2.5, right? Mm-hmm. The probability of having such a Z value or an even extreme value has a probability value of, let's say, 0.02 or something like that, right? So when you have a mean and you have a standard deviation, you can convert any distribution into Z values, because Z values basically provide you information about or give information about how far something is, how many standard deviation from the mean something is in a normally distributed data set, or under the bell curve, if you like.
Okay, so as a rule of thumb, there's no other options. Is it always going to be Z here with the whatever? No,
you can also use other tests. One way to check that is, I think I do it like this. Mm-hmm. And here you have different types of tests, right? And I actually think that a better option would be likelihood ratio or F, but you have to check because they don't all work for different models and different types of data, right? Mm. So if you read the Markdown document, I linked to basically the developers of the package wrote that you should use certain tests. Like I think it was likelihood ratio when you have categorical variables or nominal variables, and increase the number of simulations. So you need
with
which test is appropriate.
With the compare one, it seems like LR is the default?
Here,
Or
yes.
did you specify that in the compare thing?
No, I didn't specify that.
Okay, so it must take the first one, right? The L.
That's probably the
like-
default, yeah.
Yeah, okay. Mhm.
Yeah.
Yeah.
This looks like it actually allows you to test random effects, by the way,
Mm.
right?
Mhm.
But I'll have to look into that and really check what it means. Test the significance of a single random effect.
Yeah.
But it doesn't tell you how to compare different random effects, right? Yeah. So yeah, we'd have to look more into the code and what the different functions and arguments do. All right. Right. So we've done this, right? So now basically we've calculated the model for linear mixed effects model. Now we've calculated the model for a binomial logistic mixed effects model, right? And what we've done in each case is we've increased the number of participants, we've increased the number of items, and we've basically seen how that relates to power of finding an effect of in the situation that we tested, a small effect, right? And we've seen that essentially if you increase the number of items and participants, that increases power. And the question that was interesting to us was to determine how many do we need to come above a certain threshold, right? So how many people do you need in your experiment? All right. Now, oftentimes what you have is you have piloted data and you then run a model on your data, right? So we'll use exactly the data that we had here, the simr data on which this is based. But now, as I said, we will actually add a dependent variable, right? So in this case, this means that in the control, there's a 50-50% likelihood of having gaze in the area of interest and 50% that is not in the area of interest. Whereas here in the test condition, we have a 70% chance of looking at the area of interest and a 30% chance of not looking in the area of interest, right? So basically, I created a data set where there is an effect for looking at the AOI, right? By the way, I should have named this differently. I should have named this gaze or something, because it's not a good idea to have the dependent variable and the level of the dependent variable have the same name. I say so because I ran into issues because of that a couple of days ago. Right? But when I set the data set up, I didn't really care for that. All right, so now let's calculate a model, right, which really has a dependent variable. So this dependent variable is like an observed dependent variable where we really have piloted data and now we have a model, right? And that has an advantage because when we tabulate the model and we inspect it, you'll see that we actually have the parameters that we can use. No, that's great. They don't really explain anything. Oh, that's stupid. No, it's an example anyway, right? So what you can do in that case is you don't need to make assumptions about the variability of the random effects, right? Because you can actually take the ones that are reported. So that's an advantage because when you pilot data and you actually have a dependent variable, you can set up a proper model and you can then take the values from that model to really reflect the structure of the data and the variability of the random effects in your model, right? So there's an advantage to that. But as I mentioned before, several authors have said that this should be treated with extreme care because the results can be misleading when you basically perform a power analysis on an existing model, right? No matter what, I just want to show you how I can do that. Again, here I tested for the power to detect this level, right, of condition. So whether the data is strong enough to detect a significant effect for test, right? And in this case, yes, we actually are at the 80%. But of course, because we've only so few simulations, let's pump this up to at least 50. The error bars and the confidence interval is extremely high, right? Even higher, right? But that's fine, right? But again, here you get the warning message, okay, this might be an observed power calculation, so be careful when you do that. So what you can still do is you can make the best out of that by basically checking the effects here. And now you know what the size of the effect is, and you can set it. You can set it manually. So here we say that the fixed effects of model 5 for condition test, this one here, shouldn't be 0.41, which is a very weak effect, it's below weak actually, but we want it to be a small effect, right? So the equivalent of Cohen's d.2, right? Now, when we add that, we can then check the effect size again, and we get, okay, now the effect size is an odds ratio of 1.68. And now we can run the simulation, and then that would tell us, is our data sufficient to find a small effect for condition equals test, right? And in this case, basically, it shows us it's actually not looking that good, right? So our data is actually not sufficient to find an effect for condition test reliably.
Martin, real quick, so, and for the fixed F, do we use odds ratios?
In this case,
yeah.
In this case, you do. It's not always the case, right? You'll have other effect size measures for example, numeric predictors. But in this case, the easiest way is really to convert them into odds ratios, because the estimates can be very easily converted into odds ratios.
Oh, but and sorry, and how did you convert the odds ratio to 0.519?
So here I just set it. So here I see, I basically tell the model the fixed effects, or the fixed effect of model 5 that has the name condition test, which is this here, right? Should have a value of 0.519, right? And so this means, forget about this value, right? I want you to override this with this value, right? And then if we, so here we extracted the same thing for the model as they were reported. And here you see it's 0.408, so 0.41, right? Now that we've changed it, right? Now it really has an effect size of 1.68 odds ratios. So something is 1.68 times more likely to like someone is 1.68 times more likely to look into the area of interest in the test condition compared to the control condition. This is what this would, how you would interpret this.
Okay.
Right? So that's how you interpret the odds ratio.
I feel like I'm missing a thing. But...
So here we have, like, think about it this way. We've fitted a model, right? With random effects for subject and random effect for items. And the only fixed effect that we had was condition, right? Here in the intercept, it's basically the other condition, the control condition, right? And we said here that the likelihood of looking into the area of interest was 50-50. So 50% when we generated the data here. So there it was 50-50. So here the odds ratio is 1, right? So because it's equally likely for someone in the control condition to look in the area of interest or not look into the area of interest. So it's 50-50. That would be an odds ratio of 1, right? There's no effect. And here we defined that for the test condition, it's 70% probability that someone looks in the area of interest and 30% that someone does not look in the area of interest, right? So there's, compared to the control, where it's 50-50, here it's 70-30, right? And this means here for the intercept, the odds ratio is 1. It's equally likely. And when we convert this into the odds ratio, the estimate, we get that it's 1.68. No, what was it? Why is it? I'm really sorry, I'm confused here because 0.4, it should be, oh, it's the second predictor. Someone is more likely to look into the area of interest, but the thing always predicts the second outcome, the second level of the dependent variable, which is not area of interest. So here, sorry, let me make this different. I'll make it easier for you guys. Just give me a second. It'll make sense in a second. The problem with binomial mixed effects models is they always predict the second level of the dependent variable. Okay, just give me a second. And so it predicted the probability for not looking in the area of interest here, right? Okay. And now we see that here where it's 50-50, because it's simulated, we still have about a 50-50 chance. And now we see that the probability of looking into the area of interest for a condition test is 1.3 times as likely or more likely to look into the area of interest compared to the control conditions, right? Okay, now the odds ratio here is small, so it's smaller than 1.68. So the effect of condition here is actually smaller than a small effect, because we said small starts with D.2.
Yeah.
This is actually smaller than 0.2. So now we want to find out, okay, what's the probability of actually finding a small effect, right?
Yeah.
Not someone that's smaller. And this is where what we calculated here, the probability was too low. So we don't know whether the test condition really has no effect, or if it or if we don't have enough data. And we can't say that because our power isn't high enough, right? So we do the, does that make sense? Right? Okay, again, what we can do now is we extend the data. And here we extend the data along items. So in the simulated data, we can check that we had 10 items, right? And now we want to increase this to 30, like we did before. We extend this. And then we can also check how many subjects that we had. Or we can just, first of all, do this and then run the and see what happens. And that would actually tell us, cool. So if we actually have 30 participants, we would be super likely to find the effect of condition if it were small. Right? So 10 people, not enough power. And if there we don't find significant effect, we don't know whether it's because we don't have enough data or whether there is no effect. Now, if we increased our sample size to 30, then we would have enough power. And then if we still would find no effect, right, no significant effect, then we could say that's because the effect really isn't there.
Martin,
Yeah.
why can't you do that with the odds ratio that you get from the model itself? Like, can't we do the same thing and just say, okay, with the odd ratios that we get from the model, we calculate the power. Clearly, the power is not good enough.
Yes.
For example, if a reviewer says something, or if you're reviewing something and you tell them how many participants you might need more to get some power, then couldn't you skip the part where you change the odds ratio and just use the odds ratios that you get from the model itself?
You could, but if the people who write the package tell me be careful with that because it's inaccurate, I'm not going to trust the results.
Okay, but why is it inaccurate? Because you're just changing the threshold, basically, right?
Yeah, I can't really tell you. I honestly can't tell you. I really have to look at the math. And I really haven't checked the algorithms that they implemented here. And only that would essentially answer the question, I think.
And if the odds ratio was, let's say, 1.8, then we would specify effect size as 0.6 in F?
You could, because basically that would allow you to say the data would, given the data, we would be able to find a weak effect with this probability. You could also say, if you set the data, if you set the effect to another measure, let's say 3.6 or something, right? Then you would basically be able to say, given the data, we can find a moderate or medium effect with this and that probability or certainty, right? So it really just gives you the option to say, how likely is it to find an effect of a certain size given the data? That's all it does.
Yeah, I just don't understand why
you wanted to change it.
Yeah. Because if you're doing a post hoc analysis anyways, I mean, you can't, if your odds ratio is lower than the small effect, obviously you need even more than that, probably. But I don't understand if you're doing a post hoc analysis anyways. Maybe it's to avoid the issue of like, collecting data in the middle and then doing this and then saying, okay, like, let's get another 50, 60 to maybe see something, or I don't know.
I think
I don't understand the reason why they say you shouldn't do that, or like that makes more intuitive sense for me if I were to run something where like I know that my study is underpowered and I want to know, okay, how many more participants do I need? That makes more sense to me as a researcher. I mean, that information would be more useful.
I get what you're saying, but the only, like, I really haven't looked at the math that they've implemented. So I really can only say I have to trust them. If they say don't do it, then in that case, I have to stick with them. And like, if you think about in general, like the idea of power analysis, right? So the idea is really that you do it before you basically run an experiment, right? The idea is really to basically think about, okay, what am I going to do? Then come up with basically a data set that has everything the way that it's set up for the actual study, and then basically determine based on that, okay, how many subjects would I need, right? And the reason why I still think it makes sense to use small or medium-sized effects is really to say, to have a cutoff point, right? So if there is an effect that's smaller than small, right? Then why would it be my target? Like, there can be reasons, as I showed you, like imagine the nuclear power plant blew up, right? And you needed basically to to say that even a tiny effect could basically in the long term have really bad consequences, then I really understand why you would basically look for a really tiny effect. But at the same time, the effects that we're looking for, they have some sort of explanatory or predictive power, right? And when effect is really, really small, then it really doesn't have explanatory or predictive power, right? So I still think to basically say, okay, it doesn't make sense to look at very, very small effects, right, as your target. That to me makes sense. Where I agree with you is that, yeah, I think it would be great to basically just run the model on your postdoc data, right, and then see, okay, what's the power for this model, right?
Yeah.
And then basically report that, and basically say, okay, for example, for the reviewer who says, well, your study is underpowered. No, actually, power analysis shows that I could detect this effect with the certainty of, let's say, I don't know, 78 to 95% or something like that, right? Yeah. So that makes sense. But there, I'd really have to look at what they exactly implemented to tell you why they say that it's not reliable.
Okay.
All right. Actually, that's pretty much it, what I wanted to go through. So the idea that I had when I was asked to look into power analysis is so essentially Nadine and Kadish, they came to me way back, right, when I was still in Norway. And they said, well, we need power analysis, right? And so when I thought about the workshop, I thought about, okay, let's look at how the different concepts bind together, right? And then basically look at the design that they have for their experiment, and then basically check, okay, given this design, right? And you start with, I don't know, 10 subjects and 10 items, right? You then perform power analysis, you'll see, okay, the power is not sufficient if you've only 10 items and 10 subjects, and then basically extend that. So how many subjects do we need to have a certain confidence in that when you don't find an effect, it's actually because there's no effect, right? And that was essentially my motivation for showing you this, right? And yeah, what I've essentially done is I read a couple of papers and then dabbled around with the simr package and with the power package, and then basically showed you, what the stuff does more or less, right? And to help you basically use that code and just copy and paste it and use it for your own analysis. I'm super sure that there are lots of things in your model specifications that I didn't consider here, right? So for example, I just didn't think about including numeric predictors. It's not ill will, I just didn't consider it. I just, worked through my examples and worked with the data sets that I generated and then went with those, right? And also more complex random effect structures, I just didn't include them. But I think that, I think this at least should give you a starting point where you can basically, where you can take code and see what it does a little bit, and then see how you can basically apply to your own analysis. And then when you have the issue with the lists of questions and items, I just didn't consider that, when I wrote the tutorial. It would have made sense because I remember that you work with lists of questions. But the way I'd probably do that is really to take the data that you have and then probably just feed it into R, and then do exactly the same power analysis that we've done and see how they cope with the issue. Yeah, that's pretty much it.
Martin, can I ask one more thing?
Yeah, sure.
I'm trying to understand. So if you do this, you do a pilot study and you get, for instance, this 1.45 odds ratio, which is basically a smaller than small effect size, right? Then shouldn't you say, like, I shouldn't even pursue this anymore because, I mean, the effect size is going to stay the same, even though you add a bunch of participants, but then you can always say, like, yeah, but that's just because we added so many participants, but the effect size is still sort of so small that we shouldn't take it seriously. or am I?
No, I see your point. So, but it could also be like the problem here is that we can't really be confident that this is the true effect size, right? So that's the issue. It might really be that we have an inaccurate estimate for the effect size, right? So that is why we need to check, right, if we need more subjects. But yeah, if the effect size really stays low and you just basically have a p-value that's then significant, it's still difficult to interpret, right? That's essentially the same thing that that Kilgariff and Gries argued about. Is yes, if you increase your sample size, everything will become significant, but you need to look at effect size and then see and interpret that correctly and say, okay, there is an effect there, but it's not very strong. It doesn't really have a lot of explanatory power.
So why, and shouldn't we then also just focus much more on effect size than
Yes.
p-value? Or
Yes, and like what I'll do after the workshop is, first off, I'll correct the errors and send you an updated version. But also after the last workshop, I sent around the questionnaire about what we can improve and what topics you'd like to have other workshops on. And there are two things that popped up. One was structural equation models, which I actually looked into for a study here. And there are positive aspects to it. I think it's cool, but also there are some shortcomings that people should be really aware of when they use them. So structural equation models would be one topic, and the other would be Bayesian statistics. And Bayesian statistics really gets essentially rid of p-values, right? It really, what you have there is, it's essentially pretty much just effect size, right? Because you look at what's the difference between a model without that predictor and with that predictor. Like, how does it change the explanatory power of that model, right? Yeah.
Yeah, that would be, I would love to hear both those, go to both those workshops. So
there's one talk I can actually, let me just give you the link, because for the LaDAL I had Natalia Levshina. You probably know her, right? And she gave a talk on why we should switch to Bayesian statistics. And she's given a talk also explaining the Bayesian approach and gave some examples. Just let me copy the link and post it in the chat. So if you're interested into learning more or getting an introduction to Bayesian statistics and the differences and similarities to a frequentist approach or a p-value based approach, then you can look at this. Oh, sorry, that was actually not to you. That was to, there you go. So that's the talk by Natalia, I think. And then Judith had her hands raised.
Yeah, that's a related question. Yeah, my question was, so if we, move to Bayesian statistics and do not use the frequentist models anymore, then probably is it necessary to have this power analysis? Because what I could do then, if I understand it correctly, I could include this bias factor, and then it would tell me how confident I can be that my effect is really there, right?
Mm-hmm. Yes.
Okay.
Yes. I think there are some other problems related to Bayesian statistics. So when you look at, first off, a problem with the frequentist approach is that in order to assess the probability of our test hypothesis, we assess the likelihood of the null hypothesis, right? And when it's very unlikely, we reject it, right? So it's an indirect way of actually assessing our test hypothesis. And Bayesian statistics has the great advantage that it can test the test hypothesis directly. So that's really cool, right? One thing that's problematic is that that it works on permutations of the data, I think. I think that's underexplored a little bit. Because it means that you're treating the data that you've sampled not as the data that you've sampled, but you resample from that, right? And then basically get distributions of probabilities, prior and posterior probabilities. And I'm not sure whether that's super legitimate. And also when you look at the regression models now, we have so much experience and so much decades of thinking going into how do we check models? How confident can we be in their results? And one issue that I have a little bit with Bayesian statistics is that I'm not sure that the diagnostics are thought out yet, because mostly what you just do is you check whether the Monte Carlo Markov chain has converged, and then people let it be pretty much. So there's no real diagnosing. So these are the two issues that I have at the moment. It's the resampling and that the diagnostics are a little bit neglected. But I think, as I said, it's really interesting because it allows you to test the test hypothesis directly, right? Mm-hmm. And also they're becoming really popular. So I think whether they have disadvantages or not, they are something that we need to look into. So yeah, and also, was it you who sent me the problem that they had when they implemented a more complex random effect structure? They got the singular fit issue, which we all know probably. And one solution would be to use a Bayesian approach, because then that is you get rid of that issue. So there's also a reason for doing that, right? So yeah, so it's something to look into. Mm-hmm. Yeah, let's see. So it's definitely worth looking into. Absolutely. I don't know whether I would be the right person. I'd probably rather invite someone who's specialized on that, because there's people who really have done this for years as well, right? And so I'd rather trust someone who has more experience. Like with power analysis, I'm new to this too, and you see that as well, right? So fair enough. All right, bye everybody. I see that you all are leaving now, and we're over time, so we'll probably stop that here. So if you have any other questions, I propose you ask now, or we can discuss them later. No? All right. All right, cool. So then I just say sorry for the mistakes that were in there. I'll try to correct them when I send the updated version. I'll send a follow-up version, and I'll upload the videos to YouTube probably tomorrow, something like this. All right, so thanks everybody for staying with me, for figuring this out together. That was also great. That was pretty cool. I really liked that. I really enjoyed that. And yeah, thanks everybody for sticking around. And thanks for the comments, Cecile. They were really good. And I'll actually check the papers. That makes sense then. All right. So bye everybody. Have a great day. Enjoy your day. Bye bye. All right. All right. I'll stop the recording now.